So welcome back to the channel. My name is Shashank, and as you can see, I changed the channel's name. I know it can be really confusing, but I hope I won't do it again, right? So without wasting any more time, let's get into the lesson. And today we'll be talking about electronegativity and electron affinity. And there's one thing that I want to tell you about the last two sessions, right? You need not think much about last two sessions because we won't be using all those properties, all those quantum mechanical model, and then you have the classical model. We won't be using much of that in biology, right? We won't be using much of that in, let's say, any exam, but it is really important for you to understand those fundamental concepts. So we will be doing those concepts again when we come to the chemistry subject, right? The chemistry portion. But now let's stick to biology, right? Now, in the last class we discussed about shells, subshells and orbitals, right? In this video, as I told you, we are going to discuss about electronegativity and electron affinity. I know there's a little bit, only a small difference between the pronunciation of these two words, right? So, but they have a small difference between them, like all terms in chemistry do, right? So, what is that difference, right? Let me just write down what is electronegativity. It is the property of an atom to take or steal, if you want to call it that, electrons in a bond, right? It is the property of let's say an atom to steal or take electrons from another atom in a bond, right? It wants to take it, right? So let's just say that, let me just write it down in short form so it won't take much time. So it takes place only in, this property can only occur in bonds. In bonds, you can also call, if you want to, compounds, molecules, right? But in the case of electron affinity, it's different. This occurs, this property, we can state this property only when the atom is in a free state. In its free state. Okay. So actually, electron affinity is not exactly a property. It is defined as the amount of energy, I guess you could call it heat, the amount of energy released by an atom when, by 1 mole of atoms of any element, when it combines with 1 mole of electrons to form a univalent anion of that element. You will have 1 mole of these univalent anions, right? So let me just, okay, little bit, okay. It is the energy, let me write that, delta. You can depict energy by delta. Energy released when 1 mole atoms combine with 1 mole electrons to form 1 mole anions, right? Let me give you a quick example of this. You have fluorine, you can take oxygen, whatever you want to, but fluorine is, let's say, easier to understand since it is the second most, the second element which has the most electron affinity, right? So F, let me say this is gaseous. You have 1 mole of F atoms, that is fluorine atoms, plus 1 mole of electrons. This is not 1, this is 1 mole of electrons. which give us 1 mole of F minus gaseous. This is the anion here, this is the atom here, and these are the electrons, right? Okay, so we won't discuss much about electron affinity right now. We will discuss about it in the chemistry part. Right now we'll come back to electronegativity. Now electronegativity, as you can guess from this line, in bonds or compounds is relative. It is relative. This is really important. This is the one of the most important differences between electronegativity and electron affinity. Electron affinity is fixed since it is in its free state, right? It is a property of an atom in its free state, since it does not have to depend on any other atom that it will combine with. It combines only with electrons, right? So we can say that electronegativity is relative while electron affinity is not. So when we say relative to what? This is important. This is also important, right? Now in 1932 you have someone called Linus Pauling. So this person right here, this scientist, he introduced the concept of electronegativity. And what he did is that he gave a table for the electronegative values of all the elements, almost all, but I think he gave for almost all, but we're not going into how he gave it, how he derived it. That's not important right now, right? So we're going to take a look at the table which he gave, and what he took as relative, which atom he took as relative is fluorine. Now why did he take fluorine to be relative, the relative atom? This is because fluorine is the most electronegative element. This is important. Fluorine is the most electronegative element or atom, whatever. Now since fluorine is the most electronegative element, what happens is, in a compound, this will always have the upper hand. This means that this is the only atom that from which electrons cannot be taken, since it has the most power to take electrons from others, since it is the most electronegative atom. So if you have something like NaF, fluorine will always have the upper hand. That means it will always be able to have electrons revolving around it more than Na has, right? So this is important. That is why this guy Linus Pauling right over here, I should not say guy, that's informal. So this person, this scientist right over here, took fluorine as the relative atom to measure electronegativity. He took the electronegativity of fluorine by some calculations to be 3.98, 4 to be exact, but in most calculations scientists use 3.98, but we as common people use 4, or at least I do that. Okay, so let me show you the table which he gave and a bunch of other scientists gave too, right? Since I said this is relative, many scientists also came forward and gave their tables, right, with respect to other elements in the atoms. I'm going to paste it here. Okay, this is Pauling's electronegativity scale, as you can see right here. Just a minute, right? So in the first table you can see here, this is Pauling's electronegativity scale, right? Okay, this is important. Now as I told you, he took fluorine's electronegativity to be 3.98, and with respect to this he compared them in different compounds and gave electronegative differences for every atom, or at least most atoms. Since you can't, I guess, measure the electronegativity of F block, you can, but I don't think we have to go into that right now. Okay, so the next is Alred-Rocho electronegativity scale. This is another electronegativity scale, which is kind of important. But here, look at the difference. This is 4.1, the electronegativity of fluorine. Here it's 3.98. This is important. As you can see here, you can tell that electronegativity is relative. That's not really good. I'm going to do that with that. Okay, relative. That is why you got different values of the same element in different tables. Now the last one is Mulliken electronegative scale, given by, I think, someone called Mr. Robert. I don't remember his full name, but yes, okay. Now this is another important electronegativity scale which consists only of these elements, not of all. And again you can see the electronegative difference, not only for fluorine. If you take any atom, if you take oxygen, it differs. Let me look at this. 3.44, 3.50, 3.22. Right? As you can see, it differs. Let's take hydrogen. 3.06 in the Mulliken electronegativity scale, 2.20 in the Alred-Rocho electronegativity scale, I'm sorry. And then you have 2.2, which is the same thing. So in some cases it might be same, but in some cases it's not. Right? This is important. We should always remember that electronegativity, since it forms in compounds, it is relative, while electron affinity, which is the energy released when 1 mole of atoms combine with 1 mole of electrons to give 1 mole of anions, is not relative. Right? It is fixed.